this video, we're going to look at ideas for how you can think about substitution method problems, how to think about, okay, what is u and what is du, as well as how to handle more complicated ones, generally those that involve inverse trig functions. So usually for solving these problems, it's pretty easy to spot what the u you should pick for your substitution should be, right? It's the same thing like you had for chain rule. We're looking for an inside function. So your first guess for you should be, let me look at what the inside function looks like it is here and see if that works. Examples you want to think of here are things like we had a polynomial raised to the fifth power. Well, that polynomial is the inside part, so make that u and see what happens. We had stuff inside of a sine function or inside of a cosine function. We'll make that u and see if that happens. The point should be, once you make the substitution, you can integrate the result and have a formula to integrate the result. However, there are some other situations where looking at du can be more valuable. Looking to see what should du be, what do I have to make my du, and using that as a sort of argument for what you should pick for u. And so one example sort of illustrates this, and we'll see more that more heavily suggests this fact when we do the inverse trig stuff, is the following. I want to find the integral of tangent. Okay, well, as of now, we don't really have a good way to do this. We could do something like secant squared. We could do something like secant tangent, but we can't do tangent. We don't have a formula that we know of for derivatives that gives tangent at the end of it. So what can we do? Well, let's write out what tangent looks like. Right, tangent sine over cosine. So to think about this, you can either think of two things. One, what's the inside function? Well, it turns out the inside function you want here is cosine theta because it's inside a 1 over u sort of function. But that may not be the easiest thing to spot. The other thing you can do is look for du, and it looks like here's a pretty good candidate for du sitting on top. Sine theta d theta seems like a thing I could make du and see if maybe that helps me out solving this problem. In either case, it'll get you to the right answer. So if I pick u to be cosine theta, my du is negative sine theta d theta. And so when I make this change, I get a negative integral 1 over u du, which becomes a negative log of cosine theta plus c. If I'd gone the other route, I'd pick du to be sine theta d theta. I would get u to be minus cosine, and we get the same result out of it at the end of the problem. Look at this next example here. This one says integral of 4x over root 1 minus x to the fourth dx. Now your first gut instinct here might be to set 1 minus x to the fourth equal to your u. Why? Because that's the inside function. That 1 minus x to the fourth is the inside function that I see. So let's go for that and see what happens. Well, if I do that, what do I get for du? Well, my du is the negative 4x cubed dx, and I immediately see that I have a problem. And the problem is I don't have this anywhere in my problem. I don't see an x cubed. I have nothing involved at all that's going to let me get rid of that x that's going to show up in this answer here. So what can I do instead? Well, let's look for the du as motivation. And what I see up top here is an x times a dx. So what that indicates is maybe I should try making an x squared my u and see where that gets me. So let's try u equals x squared, du equals 2x dx. I can then plug those in and I get that I have the integral of 2 du over a root 1 minus u squared. But we know that integral. That there is the derivative of inverse sine. So this becomes 2 inverse sine of u plus c, which is 2 inverse sine of x squared plus c. And the point as to why this is so much harder is because it's a more complicated form you're getting to before you do the integral. It's not just a polynomial. It's not just a sine or a cosine function. It's this 1 over root 1 minus u squared sort of expression. So you're aiming for a more complicated function, so it's harder to see where you're going as you're solving the problem. Besides that, the methods are all the same. It's just aiming for one of these inverse trig forms is more tricky than aiming for a polynomial because it's not a simple expression. It is a more complicated thing. It has multiple terms in it. You need to be more careful as you are setting it up. So as a compare and contrast point, we have these two expressions here. They both have the exact same denominator. However, one's an inverse trig and one is not. The important distinction here is the numerator. Right, for this first one, I have x dx in the numerator, which means I should want to make an x squared for my u because I'm looking at inverse trig here. So I would set here u to be 4x squared because that makes this u squared here. My du is 8x dx. My integral then becomes an integral of 1/8 du over u squared plus 1. Which that integrates to arctan. So I would get a 1/8 inverse tangent of u plus c for that one. And for the second one, I see an x cubed on top, which means I'm allowed to use x to the fourth for my u. So I might as well make u the entire denominator because that one's not going to affect things. and we'll set u to be 16x to the fourth plus 1. Our du is then 64x cubed dx, which is the entire numerator. Integral then becomes a 1 over u du. So I get to log of u, and I have u right up there, so this integrates to the log of 16x to the fourth plus 1 plus c. So two different setups with the same denominator, but the different numerators are indicating what you should make your u and du to set up so that all the problems work, and that you can get to the answer when you're done. The important thing is if you don't have the du term there, it's going to make it nearly impossible to solve this problem, so you have to pick your substitution appropriately to make sure you can solve it out and get to a final answer instead of getting stuck into a loop where you can't actually end up getting to a formula that you know how to solve.